Hey, welcome back to another episode of 401 Access Denied. Today, we'll be talking to Steve Jacobs about OT, operational technology, and scientific sensors. I'm your co-host, Mike Gruen, VP of Engineering and CISO here at Cybrary, and once again joined by Joe from Thycotic.
Yeah. Hi, everyone. Joe Carson here again, and welcome back to another episode of Access Denied. And I'm Chief Security Scientist from Thycotic, and excited to get introduced with Steve. So, Steve, you want to give us a bit of introduction about who you are and what you do?
Hi. My name is Steve Jacobs. I work on a large-scale ecological science program called NEON. We have a website at neonscience.org. We collect ecological instrumentation and observational data, as well as remote sensing data at 81 field sites across the continental United States, Puerto Rico, Alaska, and Hawaii. That culminates in about 5 billion sensor readings a day. We collect about 400 to 600 terabytes of remote sensing data a year as well.
So not a lot of data. So not
much. No, not much. So, I mean, when I say ecological sensors, everything from, meteorological sensors like air temperature, humidity, and barometric pressure to things like soil water content and salinity, pH, stream flow. We have these eddy flux measurements that are really crazy that measure sort of the soil breathing with the ecosystem. And we get things from like once every 10 seconds to 40 times a second, depending on the type of sensor. All kinds of crazy stuff.
Well, so what's the use cases, kind of? So how would that data be used ultimately? Is it for agricultural reasons? Is it for weather? Is it for transportation, traffic, logistics? What's the main use cases there?
So NEON was one of the grand challenge things that were formed by NSF. The idea is that we just collect ecological data distributed to folks doing research. So we're prohibited from doing ecological forecasting or anything like that. But the idea is to use that information to validate or build models for climate change. So that's why there's such a wide variety of information that we record. I mean, I didn't talk much about the observational stuff, but they do things like trap mosquitoes, send them off to labs for DNA pathology analysis and all kinds of really crazy stuff, trying to sort of provide one place where you can get data from multiple different areas of ecology and then use that as the basis for science.
Okay. And do you use, is it all your own sensors, or do you actually bring in third parties? Because I know here, I'm based in Tallinn, Estonia, and there is a company that's based here, which is Planet.io. And they did a similar type of thing where they created a platform for basically anyone in, for example, in maritime and marine, so that they can actually take their own sensors and then upload it into their, let's say, algorithms for basically statisticals and analysis. So is it all your own sensors, or do you actually bring in third parties and others and correlate it together?
I think it sort of depends on how you define sensor. So we have our own data logging platform. We don't use Campbell loggers or things like that. Not that they wouldn't work. They would work fine. It's just that we have 10,000 of them, and they don't auto-configure, and they don't, report back and that sort of stuff. So, but for the most part, the probes and the things that are used to do the sensing are not things that we design. We use sort of like a steering committee that figures out what the most appropriate use is and what the scientific protocol is that needs to be done, and tolerances and things like that. So some things like most of our temperature measurements are done through the use of platinum resistive thermometers. And they provide a resistance measurement that's calibrated, and then those calibration coefficients are used to turn it into temperature. But we don't manufacture the PRT. We just make the cable harnesses and things that attach it. Other things like we have this ring down cavity spectrometer from a company called Picaro, and that thing does all its own stuff. But we interface with the protocol it provides to pull the data back, and there's no data logger involved. It just talks over Ethernet to the device itself. So it just really depends on what it is. We're not going to go make a ring down cavity spectrometer, I assure you.
And you don't have any third parties that are putting everything, all of those sensors. You guys basically own that stuff, right? You're not getting in. Oh, interesting.
Yeah. So there's talk of, because we have these sites, our networking team has it pretty rough. And they're basically like an ISP for customers in the worst locations.
Right.
It's not like we put one of these things in the middle of a city where people can go. There's one in the middle of Yellowstone. there's one on the northern slope of Alaska up in Kanger where there's only one satellite provider that can hit it, and it's a 2-meter dish. And when it snows, we don't have connectivity for 6 weeks. So because we have these locations and there's connectivity available, there's talk of sort of using it as an assignable asset for other programs that want to do science at these locations. So either us just providing pure transit or providing some sort of interface back into our system for collection and distribution. It just depends. Hasn't really been sorted out yet. We have sort of our first co-located experiment coming online or being worked out right now, but nothing's been formalized.
Okay. And so from the sensors side of things, what types of connectivity, because I think really when we get into and we're looking from a security perspective, when we look at, all these devices, one thing I've been used, to in my past work is when I'm working on, I worked in a lot of maritime. So we had a lot of, let's say, buoys that were actually, pulling back sea data. We had a lot of, shipping containers that would tell you the temperature and the moisture in the containers so that, if food was going off or cold or whatever. So we can, from a shipping perspective as well, and also from a mining perspective, is mostly for coordinates and data about maintenance and performance of the machines and the trucks themselves. So we're seeing a lot of different kind of data coming back. And for me, one thing is it's all about when you talk about different sensors and edge devices and different kind of areas where they're basically just picking up one piece of data and then communicating it. What's the medium that you're using or seeing? Is it over things like Bluetooth? Is it over Wi-Fi? Is it using, let's say mobile carriers like 4G or 5G? What type of communicate? What type of standards are you keeping to, and what are you seeing that's being used? So
for the most part, the design that was built for Neon predates me, but there was a desire for providing power to a lot of these types of sensors. Like that PRT needs voltage. And so the data loggers themselves are all built to run off PoE. So the whole entire site is basically PoE powered. And then the data loggers do DC to DC conversion for different voltages. So 24 volt, 5 volt, 3.3 volt, depending on what type of things are attached. And that's most of the instrumentation. There are some things like you mentioned buoys. We get a buoy, I forget the name of the manufacturer, but they have their own design that has like pluggable modules for doing different water quality measurements and things. And that has a wireless radio that comes back to one of the data loggers we have on the shore. And I believe that is LoRa or something similar to that. It's not Bluetooth, but it's some industrial protocol that they use as a serial, basically a long serial port to pull the data back.
Okay, it's a pretty long cable.
Well, yeah, I mean, it's not no cable, right? So,
right, radio, right.
Yeah, I mean, the problems they have with that instrumentation tend to be, high flow events and things that tend to be more frequent now than they used to be. So stuff washes away, or they need to do something to moor it, and then these things tend to be in like national parks and places where you can't just like dig and put a big concrete buoy somewhere. So you have to get agreement about what can be done.
And what about so all of this data is being generated, and the frequency is quite impressive because the frequency of the communications I was working was much less frequent because of power consumption. The more frequent you communicate, the more power you use, and these are very power sensitive devices because they're meant to be very low power. Consumption. And I think that's one of the things I'm seeing. The advantages of at least 5G coming is 5G definitely has power advantages.
Doesn't help me though. I mean, 5G is not where these things are.
True. True. So what type of security things that put in place? Is there any security at all for those devices? And when we're talking about a lot of these, if you're talking about serial cables, or we're talking about Bluetooth or wireless. A lot of those I tend to find in the environments I've worked in is that they tend to have no security or no encryption because just the loss in bandwidth is significant when you put in place. And then what happens is it means you need a much more powerful device in the end to be able to manage that. And again, that means more power consumption. So what types of security is put in place in those devices as that you're using?
It's it's basically what you're saying in terms of folks weren't thinking about security when this stuff was engineered. To the point where, like, a lot of the instrumentation is just sitting out there. You can plug into it. It's not even in a box. They were very concerned about environmentals for this stuff to make sure that it could work up in -40 in Alaska and in Arizona and that sort of place. So magnesium or aluminum casings and very high temperature ratings and that sort of stuff. I think part of it just comes from a maturity of understanding what people mean by security. So if you went to someone at my program, 5 years ago and you said, "What are you doing for security?" They'd say, "What do you mean? No, who cares if people steal the data? It's public data. Our job is to distribute this data to everybody. So if someone comes and gets it, I mean, what's the big deal, right?" But if you think about it, like in terms of the CIA triad, right? We don't have a high confidentiality requirement. The data that we retrieve, it's going to be publicly available anyway. There's some quality measurement and aggregations that are done for time periods and that sort of stuff. But some of them have some more complicated calculations that have to be done for derived data. But there's not really much of a confidentiality requirement. But when you look at integrity and availability, those are pretty important. And I think availability has been fairly well handled in the design. We don't care so much if the data is late,
right?
But we do care that we have to be able to process it if it comes late, which sort of presents us with a different design and different concerns than a typical like IoT type thing. My thermostat in my house reports back the temperature in my house to ecobee, but if it doesn't do it for 3 days and the 4th day it updates, ecobee doesn't care about the last 3 days, not really, right?
But time is important. Time,
so we care about keeping all that data. So there's sort of buffering at every level of the design. Data loggers buffer in case they get disconnected from this computer we have running each site. Those things are designed to buffer for at least 30 days, and then that sends data back. So all the availability pieces are done pretty well. Integrity, though, I think is something that's just not really adequately thought about. And it's a difficult problem for sensor networks like this, because I think fundamentally it all boils back to provisioning issues. You can handle the cryptography overhead and that sort of stuff. It's not really that bad, especially when you start talking about using something like protocol buffers or Avro or some means of bulking and batching and compressing data for like something like Kafka or something like that. There's ways to get the bandwidth down. But if you're going to do any sort of keying or signature outside of just like a CRC or hash, you have to have some way of providing a root of trust at manufacturing that you can leverage for bootstrapping, and that's not really a solved problem anywhere. I mean, ignore the sensor space, for instance. It's very similar to the messaging space, right? Just you think about you're sending messages to other people, and Apple, they seed their phones with a root of trust, and there's a way they can derive keying from it, and they use that for iMessage. But if you're another messaging provider on top of that, that doesn't work. So you need to either leverage those mechanisms to store secrets and end up deriving trust back to a phone number or something for bootstrapping. And for us, we would have to inject some sort of key material or public key or enrollment key or however you want to look at it in order to sort of chain that whole process off. And it's sort of a complicated question about how best to do that.
And I think it also comes into so data integrity is the important part, right? And then it's also a question of, well, what's the risk, or I imagine at the individual sensor level, an attack against a specific one sensor isn't going to mess up. I mean, you guys are collecting so much data. I mean, maybe I'm wrong. But what would be the sort of scale of the attack, or what would be I think you have to sort of think it through from that perspective. Like, what would be the point? How much would they actually have to compromise in order to have any significant impact? I imagine most of the algorithms that are being used on the data that's coming back from these sensors are imperfect. You're probably right. So you probably already have things built in to throw out like, this is an outlier. So how many would you actually have to compromise? How much data would you actually have to compromise in order to compromise the system?
I think you're hinting at it here, right? It comes back to threat modeling. Like, what's the actual threat? And I think for us as a program, ransomware is a far higher threat than someone modifying sensor data, coming back into the observatory. It's just the motivation is just not there.
I mean, if I'm ExxonMobil and I don't want people to believe in climate change, sorry.
I mean, that would be difficult. I mean, it would be difficult for you to figure out exactly what you would need to modify because we don't do forecasting on that data. It's not really well defined as a science yet. So we're just collecting information. So you would have to have the foresight to know what models would be built off of this data to then know what you would want to modify to get that desired outcome.
Oh, I would just replay the data from 10 years ago so it looks like everything's steady state.
No,
I know.
Yeah. So going back to Mike's point as well is data poisoning. So it's from an integrity perspective, that's one of the biggest risks. Is that and Mike's kind of going to is that how much data poisoning do you need to do for the rest of the data become invalidated, or that the accuracy of that data becomes seriously impacted. You're looking at if you only need it's like going into you've got let's say threat feeds. In security, we use a lot of our risks based on the threat feeds coming in, and how much of that threat feed do you need to poison in order for you to get too much false positives that creates distrust in the result itself. So we discussed the same. Mike, we discussed the same around the election side of things. How much distrust do you need to put in the system in order for people to lose the trust in the system itself?
Right. So I think that, to some extent, when you talk about information security, a well-secured system is also a well-running system in many regards. Mm-hmm. And you can use cryptography to improve, remove errors from your system. If there's no authentication required at all for a sensor to communicate, how do you know that it's even in the right place? That it's the right type of sensor?
And the same.
Right. Yeah, the same thing. So not having any mechanism to do that leads to errors. And those errors lead to decreased availability, right? So there's still a need for those sorts of mechanisms just to ensure the quality of what's being collected. The question is, where's the line, right? Where is it appropriate? Right. And in my case, this is a program funded by the NSF. I have to justify every piece of the budget, and there's always tons of work to be done. So is there money available to go build these new mechanisms, or do we want to concentrate on this other problem that we've got that's pressing? Yeah. It gets, it's just triage, right?
Right. I mean, that's what security is, right? It's always that threat modeling. It's always that trade-off, right? If I had unlimited resources and unlimited money and unlimited time, obviously I would secure things well beyond whatever, but I have to look at what's the data that I have, what's the risk if this data
probability and likeliness.
Right, exactly. Whether it's corrupted data or public, in your case, you have the advantage of it's all publicly accessible data anyway. So that makes one side of the equation a little bit easier.
So your point, it's the two things. The two biggest risks is availability. Is that a ransomware threat is a true risk of not making that data available, even if it's publicly available. If the service is not there, then that's a risk. And then integrity, creates distrust in the accuracy of the information. So since it's already gone public, then it's about encryption. Confidentiality, as you said, doesn't make sense. Now, I get into one of the things when I'm always looking at these edge devices and sensors, and they're communicating in, and it reminds me of one that I worked on. I'm getting old these days. It's now 6 years ago, so it's getting longer. And it was when I first interacted. I was doing a penetration test quite a number of years ago, and it was in a ship management company. And ultimately, what happened was they had light bulbs that were actually deployed, and simply those light bulbs, were connected to the internet and connected to a Wi-Fi access point, but they were directly connected. They were not segmented. They were not having any dedicated, gateway or correlation point. So it meant that as long as they can access any access point, therefore, basically, you could intercept the communication. You can, ultimately, what we were able to do was also make a Raspberry Pi pretend to be a light bulb because we're able to actually simulate the communication. So, from let's say a scale side of things, do you look at correlators and gateways for these devices, or how do they ultimately, how does the data get correlated together? Because for me, I think in these areas, the biggest risks is not the device itself; it's the aggregation point of where they actually come together. And I think that's where really, if to look at security measures, that's what really needs to be emphasized. Because even the light bulb itself, the vendor, when we notify the vendor of the risks and the vulnerabilities, they end up coming and creating what was called as a smart hub. And these then devices were not connected directly to the Wi-Fi access points. They connected to the smart hub, and it was a smart hub that was connected to it. And that provided the protocols and additional controls, because then those aggregators and correlators became more powerful. They had more power, more energy, and more connectivity. So what do you see is the risk in those areas? Do you have similarities?
Well, I can talk about what we do. And part of this is just because we had to design this system to survive communications failures for long periods of time. But we actually have a dedicated computer at each site that is basically a full-on Linux box that we can do this with, and it coordinates all the collection activities and buffering, and then everything that gets sent from the site gets sent from that system back in. Similar to what you're talking about with the gateway, just a much higher powered version of that. And we're currently working on a next generation design for that is tremendously more secure than what we were doing previously, has much better software update mechanisms and that sort of stuff.
You don't have to drive out to the site to update it.
Well, we don't have to do that today.
No, I know. It's just
when you start talking a fleet of machines and spotty connectivity, so you can't do something like run an Ansible playbook and have it hit every box, in an expected way. You have to, and then introducing things like maintenance windows where you can actually do an update. But I think the challenge that I see is really on the communications protocols that are used for these sorts of devices. And if you look at CoAP or MQTT, the messaging format is fine, but ultimately, if you want to authenticate a device when it comes to one of these systems, the choices are not particularly great. Built in, there's usually username and password, and if you're lucky, those passwords get hashed on the back end. In a good way. I mean, most of them hash.
But the password's password anyway. So what is it?
Yeah, it's the same.
There's no scalable way. There's no scalable way to do username and passwords for millions of devices.
Right. Obviously,
that's not useful. And then they usually have some sort of support for MTLS, right? Which you can build a scalable MTLS implementation, but it's a ton of work. And if you don't do things like handle revocation through some robust infrastructure, then you're in sort of the same boat you were before. You can't move things around and they expire, and renewal has to be handled and all that kind of stuff. And then if you look at newer systems, assuming, and this would probably work assuming that you have an online system, they're all using sort of a bearer token type setup where they go to like an OIDC type service, and then there's a bearer token, but you still have this provisioning process that you have to get through where how does the device get the bearer token and renew the bearer token? The authentication problem for devices that you ship out and don't touch and then come back in is a tough one. Back a long time ago, I used to work doing some government security stuff, and the way that they would think about things, for voice, would have a lower standard than something that was automated. Because with voice, I've known Mike a long time. I'd recognize Mike's voice, so if he's confirming to me the authentication is working, I know it's not being intercepted and changed because I can hear Mike's voice and I know what he sounds like. But machine-to-machine communication don't have any of that. And so there's a higher standard to
peer trust. It's all about the peer trust is having, I remember, getting into a lot of discussions because one of the main areas I work in is identity and access management and privilege access. That's one of my main fields. And one of the things is that it's about, as you mentioned, even when you talk about the Apple side, it's about how you verify the root of trust.
Right.
And how do you bring people into that trust? How do you provision new machines? Because provisioning is always for many companies. That's probably the biggest challenge when you're bringing new devices in. Does this device know that other device? Are they introducing you to something that they're already familiar with? Has it got similarities? And I think it reminds me always when I go back to even one of the old Windows licensing mechanisms, where that's what sometimes we always go back to is that old licensing mechanism where basically the license was built off 5 hardware components that was on the device. And if any of 3 out of those 5 components changed, then the license was invalidated. And that ultimately kind of gets into that same, the fingerprinting side. You take it off the serial number of the hard disk, how much memory is installed, the CPU, and you basically combine those all together. You get an ultimate hash, and then if that hash becomes too distant from the original source, the 3 components get changed, then the license becomes invalidated. And ultimately the same thing.
Right.
Yep. Yeah. So it's ultimately the same kind of mechanism we need to make sure that one is we have self-provisioning capabilities, and also having the ability to have trust parameters that allows these devices to self-provision and gain access, as long as they meet these, kind of set controls that kind of verifies where they're from. And it could be the same, from a mechanism. I remember even, what was it? TPMs was the same problem. They had to come into central locations. You had to put the keys on it. And then, in these depots, before it goes to its destination, because provisioning was always the biggest problem. Right. And I think, that's probably, if you do solve an identity, challenge, then the biggest problem you end up coming down is provisioning, enabling, and do you have these depot systems that has to go to before it goes out to the site?
The way Microsoft and other people get around this sort of thing is with an activation key that can only be used, a certain number of times, or some sort of business logic rule attached to the activation that is then derived, and maybe some sort of internal hash for the value so that you can detect typos easily or something, all that sort of stuff. And I think that works fine from a consumer-facing application, but not so well for some more industrial type applications. It just gets difficult. And then manufacturing-wise, we have a manufacturing floor where I'm at, where they do cable harnesses and that sort of stuff. But how am I going to get them to do controlled key load in a way that doesn't leak it accidentally? And they can barely get some EPROMs programmed for IDs off of some barcodes. Like the doing that sort of thing securely would be a huge training barrier.
Right. And back to the other point, probably not worth the the cost. Just isn't worth the squeeze. And it's funny, you're talking about your system, and we've talked about OT in other contexts, right? OT security, and I think one of the common threads is how much is over these serial protocols and the lack of security there. And basically, what you have is not that dissimilar from a giant car. But unfortunately, your wheels and your steering wheel and your sunroof and everything are just
we don't have any CAN bus, in this sort of application.
Well, that's true. You don't have the CAN bus, but but in terms of that sort of serial, that's again at the heart of it is that's. And I think when we talked to when we talked about that, it was, well, what can we put on top? Because we're not going to change those protocols. We're not going to change.
No,
it's what can we
really
design.
Tricky.
We're not going to change TCP and Ethernet. Right. Those are not going to change.
Yeah, but the industrial equipment manufacturers try to do that all the time. There's EtherCAT, right? I mean, it's not just us talking about that. And when you start talking about a car or factory equipment, there's a life safety aspect to it that I don't have to worry about in the system I've got. But once you start talking life safety, now it's the folks that design these industrial protocols, they weren't dumb. They were thinking about that sort of stuff. But what they were thinking about was, well, the robot arm needs an update every 20 milliseconds. And if it doesn't get one, it'll fail into life safety mode and move the robot away and stop moving. But they weren't thinking about somebody manipulating that. They were just thinking about, if the equipment fails, what do I do?
Yeah. And I had a big conversation when I worked in a project a number of years ago, which was an autonomous shipping project as well. And this was a similar scenario. It was about, there was not so much about life and safety at the time, and it wasn't about, encryption and confidentiality. It was all about availability. When you put ships into the middle of the ocean, it was about how well those, components perform without human intervention. How long can they go?
Right.
And it was a big discussion we had over things like LNG. Most ships today are running gas, and therefore basically lighter fuel. Therefore, they get longer distances without, from a weight perspective. But with an LNG engine, they're heavily kind of human needs to maintain them. They're need more maintenance. So, people, they can actually have in the vessels to maintain those versus things like diesel engines where it's more heavy fuel. And therefore, but diesel engines will run for hours and days without human intervention.
Right.
So there's always that balance about trade-offs. And it got into, there was a big discussion when we were looking at autonomous shipping side. And, we had similar issues around connectivity and bandwidth. When you have a storm or a satellite goes out of direction, these were heavily dependent on things like GPS coordinates, DPS, VSAT links. And, you've got, of course, multiple systems to make sure you have high availability of communication lines. But ultimately what they end up getting into as well, and there was a patent eventually done, which was using a relay system, was, to make sure that, if you lose connection back to your main, let's say, path, that you could relay it through other paths, other vessels in the ocean. So, rather if you lose connection with the satellite, what you could do is relay it through another ship that has a connection. So, is there innovations that you're doing or that looks at these higher connectivity advantages, and especially those places that have poor communication? As you said, if it was in Alaska or in the ocean, where bandwidth is at a at a premium, where do you see the kind of improvements of availability?
Well, we don't do anything like that for any sort of mesh topology or anything like that. And not that it's something that we couldn't do, but there's not really much of an advantage for the way that our sites get deployed in doing that. There's not any sort of anything nearby in some of these places at all. And if there is something nearby, we're looking at leveraging it for connectivity more than anything else, just to get the cost down. That satellite provider in Alaska, there's actually not a bandwidth problem when it's online. There's plenty of bandwidth. It's just very expensive because they're the only provider that can hit that.
Monopoly. Yeah.
So and that's your only choice. You can't go to Viasat or something and get a cheaper connection. We do that other places, and I was talking to our networking guys. It's really only about 10 sites we have that have those sort of really tight constraints. And some of them are really difficult because there's an absolute cap. Like we can't send more than a certain amount of data a month, period. There is no option for buying more bandwidth. It's just not available.
Right.
And then there's another set that are all cellular that, they're a little more expensive, but there's not really a cap. And then we have hardline fiber to a lot of sites because we end up having to run hardline power. You have to run power for 20 miles to get somewhere, and might as well run fiber while you're doing it. So it really just depends on the site. But those mesh topologies are always interesting to me because they're always talked about in the context of providing greater availability. But as I'm sure the more complexity you add, the more risk you have to availability. You want to make a high availability web service. Well, that's probably going to take a lot of testing. Your deployments are going to take longer. There's going to be more complexity in that solution than it would be if it's just a simple setup. And you really have to ask, how much does downtime cost me? Is it worth it? It comes down to economics, just like everything else, right? How much does it cost me? Is it worth the extra complexity to enable it? What would my cost be if this didn't work? And is it worth the exercise? I think in the case of that ship solution you're talking about, it was worth it.
It is worth it. Because if you lose connection to ship and it takes 2 miles for them to stop or turn. It's not a lot of time you want to wait for that connection to reestablish again. So, so those things, as much
there's probably an Iridium connection and a VSAT connection, and correct. And there's probably failure modes that go to lower bandwidth when you hit Iridium. We're looking at using Iridium next, actually, for one of our sites.
Okay. So that's a lot of the providers are using K-band and L-band types of connections, and got a lot into it.
Alaska.
It's an interesting, because even how much speed you would be, the speed that you get through those is so slow. And I think that we even look back at, I think probably sometimes slow connections is good. That's if we look back at even at the ransomware cases with NotPetya, Maersk were probably really happy that their server in Africa had a really slow connection because it wasn't possible to get infected on time because of that poor bandwidth, and ultimately end up saving them being able to use that domain controller to restore the rest of the environment. So they were quite lucky and fortunate. So sometimes low bandwidth connection can save you in the end because they become very difficult to impact as well from a tech perspective.
Right. That's another challenge we have on the bandwidth side is just our data hosting and distribution. The instrumentation stuff that we're talking about here, it doesn't actually take up that much space. When I talk to folks that are trying to understand it, they ask, well, how much sensor data do we get a day? And I give them that number, 5 billion readings a day. And they're like, yeah, but how many megabytes? How many megabytes is that? I'm like, well, no one asks Visa how many megabytes the transactions they conduct a day take up. Like, that's not the figure that is crazy. It's the individual measurements that have to be processed and handled. It's not the size, right? On our remote sensing platform, we fly this plane. It's got a hyperspectral imager, a camera, high resolution LiDAR return. We fly each site once a year and produce a bunch of data, like they look at like foliage coverage and the hyperspectral imaging and that kind of stuff. But an individual image from that camera, it's a 100 megapixel camera. So one image is like 28 megabytes or something, compressed. It's one piece of data in the other context, right? So, that in that one, the size is relevant. But the problem I have is I have people that want to come in and download 4 years of that remote sensing data.
Right.
Next week, and they won't tell me, they just want to get it. And it makes it very difficult, pricing, cloud hosting or bandwidth and that sort of stuff, just to try to accommodate the use case for the data. And we expect that use case to increase over time.
Yeah. Do you also have to compete with bandwidth from other services as well? Because one thing that I find quite often, working, it was oil rigs. Whenever a helicopter was landing, because of the safety aspect, any other communication we were doing, sensor readings, we had to switch it off for that helicopter until that helicopter landed. I also had major problems in vessels where all of a sudden we were doing some engine diagnostics, over the VSAT link, and we're looking at this data, and then all of a sudden, boom, everything disappears and connectivity is lost. And we're going, what was happening? And we end up finding out that it was the captain decided to make a Skype call to the family and used up all the bandwidth. Do you end up competing for bandwidth? Do you have dedicated or shared links?
The problem we have tends to occur at sites where there's no cell coverage.
Mm-hmm.
And we have field technicians that go out there to do work. And those hyperspectral, not the hyperspectral stuff, the ring down cavity spectrometers I was talking about, they're, like a lot of other industrial equipment, they have a Windows 7 computer attached to them that manages the system. And it's online, and it has to be online because the manufacturer supports it through TeamViewer.
Oh, wow.
Okay.
That's great, right? So people were like going on Facebook on these systems because it was the only computer out there, that was hooked up. And so they'd get on Facebook or, watch a video on Facebook or something, and then the whole site goes offline. Somebody
that's experience I've seen. I've seen similar,
that's the sort of stuff
scenarios.
that we run into is, someone does something and there's very limited bandwidth, and, they go, oh, look, this works.
Yeah. So I think there's the benefits and the negatives. It's right. When most of the negatives is likely it's our own self-infliction that we end up causing the problems.
So what we've done is we put a wireless access point at the environmental HUD that they can get on, and it's prevented from eating all the bandwidth if they want to do something, and they have a laptop so they can hook it up. So if you try to fight that to keep people out, I found that people will find a way in. It's just
right. That's like I think that's another theme that we found when talking to anybody in security is right. It's like you have to come up people will find a way around your draconian policies.
Oh, yeah.
So it's better just to figure out a way to make it so that they can do what they want to do in a secure way that doesn't impact and doesn't do this. You're just better off than trying to fight it, because otherwise you're just going to be standing on the sideline yelling and screaming, what are you doing? And the game just continues.
You might find it worse.
It's like an architect complaining. Yeah. It's like an architect complaining that the office would be beautiful. People just didn't come in and mess up their desks. It's the same problem. It's if they just have these damn users on the system, everything would be secure. They wouldn't click on all these email links. Like, well, no.
But that's their job. That's ultimately what
that's literally all their job is.
So, and I think that also gets probably back to one of your bigger challenges, the ransomware attack, right? Now these people are using these Windows 7 machines that are out there for a very specific purpose. And that purpose isn't social media.
Oh, so and they have to be on the internet, because that's how the manufacturer supports it. Okay.
Right.
And I can upgrade them to Windows 10 for $10,000 a piece.
Wow.
And we have 100 and some of them.
And you'd be still vulnerable, but not as
right. You just be vulnerable. Right.
Well, so we have another system that is also Windows 7 that is completely unpatched. Like, it's Windows 7 from the first release of Windows 7, and it's needed for scientific process, and it's not an uncommon problem to have. Right. It's just not on the network.
Right.
Well, don't put it on the network. You have to put mitigations in place. I know someone. We have someone on my team that used to work for Gates Manufacturing, and all of their manufacturing line equipment was like Windows NT until very recently, right? and they have to keep that running because it's billions of dollars of revenue attached to that stuff. But you have to mitigate the risk of running it. You can't just like plug it in and go, oh, nothing happens.
Well, right, and that's one of the other challenges, right? Is as these systems that were never designed to be online or put into context where maybe they can be, or even an air gap network, there's still problems with that. There's still the potential for, even if it's not on the system, there's still the potential.
The first problem is most people don't know what that actually means.
Right.
They say air gapped and they go, oh, it was a firewall?
Yeah.
That's what people think. They go, oh yeah, it's just firewalled off the internet. It's air gapped.
Right.
No, that's not what air gapped means.
It's not even one.
Or outside, government spaces, it's a little different, right? DoD type stuff. But commercially, what's the temptation to go? Oh, well, I just need to download some stuff to this thing real quick.
Right.
If it's got a keyboard, it's got interface ports, and it's connected to a network, it's not air gapped.
Right. If I have physical, my definition is if someone has physical access to it, it's already.
Yeah.
If you have a USB port.
Yeah. If it has a USB port. And I mean, I've seen this a lot in the maritime, my experience in maritime industry is you've got Actis systems running in bridges of ships, and people plug their phones in to charge their phones into navigational equipment.
Yep.
And end up infecting them systems.
Right. Unless you epoxy all the ports shut.
Yeah,
which
we end up having to do.
Right?
Yeah.
Right. On the plus side, Steve, Windows NT doesn't support USB devices. You have to have like a PS2 keyboard.
Well, actually, that was one of my points. The older the operating system you go back, the less problem it is to actually impact today, because there's not many people who know around, and there wasn't many exploits at the time as well. Right. They were actually quite challenging.
That's why you run BSD, right? The IP tables command doesn't work, and
so we run everything off of Apple IIe's here. That's
well, all your son pizza boxes, Mike.
Yes.
No one will know how to get to /user UCB.
I still have a bunch of OS 2 running,
so you'll be fine.
Exactly. But I mean, it is. I did work at the National Library of Medicine for a while, and it was interesting talking about. I mean, not from a security perspective, but the notion of like these digital archives, and what does it mean, and like to preserve something, and the fact that you had to preserve, like if you had a digital file, like do you constantly upgrade it to the latest standard in order so that you can read it, or do you keep these old computers around that are still able to read those older things? And sort of that same thing, like if you go, there are things in the world that are so hard to talk to these days that even though they're completely insecure, it's just so hard. It's security through obscurity, essentially, because it's just not, there's not many of them, and it's not worth the effort.
The lowest common denominator format for us right now is CSV for a lot of things.
I mean, I think that's universal. I mean, I think there's a reason why every job I've ever worked at, I've written. This is the first time I've ever had a job where I haven't written at least one CSV parser. Usually it's 2 or 3. There's a lot of benefits
to not being CSV for a lot of these sorts of data sets. Columnar formats have a lot of benefits.
Right.
And we use them internally pretty heavily, but in terms of what we publish, we don't currently expose that stuff. And we got a lot of debate going on internally about whether it makes sense to sort of dynamically convert from the columnar format to various formats people might request or what. And then even in the proprietary accepted formats like that, the remote sensing stuff like the hyperspectral imagery and that sort of stuff, that changes too. We're using geotiffs for most of that imagery, but now everyone's moving towards cloud optimized geotiffs. So do we want to make that shift or not? It's constantly upgrading the data format. I think at some point you have to sign up for that.
Right.
But then what does it mean for the old? Do you keep the old one around too? Is there money to keep an extra couple petabytes around? It's not exactly free.
Just convert on the fly, man. Just convert on the fly.
Yeah. Well, so actually that particular one is pretty interesting. So the only difference between GeoTIFF and cloud optimized GeoTIFF, they're the exact same format. So they're both GeoTIFF, but cloud optimized GeoTIFF is restructured to allow range requests.
Right.
So you can actually view parts of the image over HTTP as opposed to having to get the whole file.
Having to get the whole file and look at it,
which also makes it bigger.
Oh, interesting.
Because the compression's not as good.
Right. You can't do as much compression. Right.
Which again comes down to the bandwidth issue.
Well, actually, in this case, it's data storage, right?
Right, storage, right. Well, storage is cheap. I mean, we all know that.
Yeah, it's always the case. Every question you get into that I've always done in infrastructure design architecture, it comes down to storage and speed. Right. and you always have to decide which one, do you want? And I think that's actually one of the things I've seen here in Estonia was, one of the reasons why they're moving to 5G much faster is that they don't need to move the data as much. The data can stay on the edge devices. And what they're now doing is they're using that higher bandwidth. Yeah. So to ask the questions that they want, rather than saying, let's bring everything centrally, let's leave the data out there and we'll ask it when we need it.
What's that project? It was a former Facebook project that got spun out open source that provides like a SQL query engine across your cluster of machines, and you can get dynamic responses back. Can't remember the name of it, but it's similar to that, right? You run the query and the query gets distributed across the whole environment, and then you can get your average CPU consumption, off the whole thing. You don't have to store it. It just pulls it back from the machine itself.
Correct.
That sort of approach.
And it's ultimately what I find as well is that, I've done a lot of things like immersive VR types of things as well, where that became an advantage where now what you're doing is that you've got these machines. Yeah, you've got a device which is actually sending it faster and quicker to the central storage over 5G, and therefore you have less battery consumption. So I don't need to walk around with a computer. I can actually just have a very lightweight sensor that will actually send it very quickly across. It's going back to the old mainframe scenario. The dumb terminal that basically just you're only doing is putting characters in and it's getting processed centrally. So there's a lot of benefits. We are doing that pendulum swing again, back and forward, because of improved connectivity and being able to query. As you mentioned about the algorithms that you can query out to those devices and not need to bring all the data centrally as well.
Right.
Yeah, that's what we're looking at with this next gen design for data loggers. We're looking at is these new SoCs that they're much faster, and so the amount of time you spend doing processing is so much smaller that the power consumption, even though the theoretical power consumption could be so much higher, your processing needs haven't increased, so you're actually using it so much less that the power consumption is so reasonable.
And it also gets into benefits against it, reduces your risk against things like ransomware and denial of service attacks, because what happens is that you're still keeping your data decentralized, and what happens is that it becomes much more difficult to target from both an availability and an integrity perspective, because then you have to target all of those sensors and all those devices. So it's one of the practices that Estonia done, and we've discussed, Mike, several times about Estonia's method. What they do is they don't centralize all the data repositories; they keep them decentralized. And what they have is a message sharing algorithm that allows you to ask the questions that goes out in real time and gets the data from all the boxes as you need it. So there's benefits of doing that, because there's also the side effects as well. But it does mean that you have to have good bandwidth connectivity.
The challenges for us are things like those buoys, right? They require field calibration for the most part. So every 2 weeks, someone has to go out with like a little pool kit, and make sure that the measurement for the science they're trying to conduct, they need a certain amount of accuracy. So they have to do that on a regular basis. And that information gets logged back in to the pipeline that does the calibration and conversion, but it's always delayed, right? Because if someone goes and does that calibration in the field, right now, it'll be at least a few hours before there's somewhere where they can actually enter in the data somewhere as a result. And the buoy doesn't have any interface for logging it directly into the buoy, because in the model you're talking about, that's what you'd do. You'd log it into the buoy. It would do its own calibration based on what was going on, and you wouldn't actually have this downstream system that you'd have to worry about. And so now you've got 10, 20,000 of these systems all doing their own independent piece, and there's not one place to attack or manipulate.
Correct.
But then you have to maintain 20,000 discrete systems consistently, and it's a different problem.
Then that becomes the identity and access piece becomes very critical, important. The access controls for all of those.
So there's a project you might be interested in called Waggle. Apparently, Waggle is the dance bees do to say where the honey is, or the flowers are to go get something. And so these folks had an interesting idea, which is an edge compute type approach. So at least the original system they deployed, they have a camera attached to an embedded, SBC type system, and they want to count bees. And so they use a machine vision application that counts bees that go by on video. And It's probably not 100% accurate,
Right.
but it's more accurate than not counting NEVs.
Right. Right.
Because that's the other choice.
Right.
And so they're just sending back the V count, not the video feed back across, some crazy link and retaining it and everything else. And that's it's an interesting way to approach it, is to say, well, the science we can do with that data is better than no science.
Right.
And, we can improve the algorithms over time and get a better idea what's going on.
Yeah. It's similar to the contact tracing that Google and Apple have done. The same concept, decentralized edge, contact tracing, where basically they're just, creating unique identifiers, sharing them with the devices in proximity, and simply, uploading that to a central database for tracking and alerting. So anything you do on the edge, I always find is, it's better long term. Ultimately, the less data you have decentralized.
Yeah, and the other thing I think, Steve, you're talking to is also the idea that, like, usually getting 80% accurate that's relatively easy. It's that last 20% that's always really, really hard. And usually 80% accurate is actually really good. If you look at, like, sort of the math of, like, how much harder it is to get more accurate, and what does that better accuracy actually result in, it's so diminishing returns that, these types of systems, especially when you talk about scientific systems that are massively distributed, so you have lots and lots of nodes, the accuracy.
I'm going to use some military terminology here, but I'm going to talk about my program, okay? I would divide data needs for my program into two classes. There's strategic needs, and then there are tactical needs.
Right.
So strategic needs are the goal of the program. It's a 30-year data repository of ecological information. Someone needs to be able to come in year 30 and ask for a 30-year history of soil temps at one of our sites, whatever it is they're trying to research. So it's a very sort of strategic resource. It's for long-term planning. It's needed over a long period of time. And an edge type approach like you've described, I don't see any way to make that work to meet that strategic need.
Yeah. Right.
However, there's another need internally, which is a tactical need. Oh, and by the way, that strategic need, if it takes me 3 to 4 weeks to provide data where there's a 30-year tail on the data, no one's really concerned.
Right.
They want to make sure the data is of high quality, that it's got all the things applied that it needs to have. And if it takes longer to assure that, that's more important than the speed at which you can have that data. Right. On the strategic side,
you mean the tactical side?
Sorry, the tactical side. Thank you.
Yeah.
On the tactical side, I need to run the observatory. Okay. If someone unplugs something, and that means that I'm getting 0 measurements back from a sensor, and they're only at a site every 2 weeks or every month, I don't want to wait a month to fix it. I want to know immediately, as soon as that happens, that there's a problem and that they can go fix it. I want to shift those problems left, right? Just like we always talk about for engineering, right? I want to have, as soon as the problem occurs, I have a very latency sensitive need to know there's a problem or there's a change in instrumentation. If someone has calibration coefficients for one of these thermometers that starts showing it's 90 C outside, and that can't be possible, I don't want to publish data with an incorrect calibration. So on the strategic side, I don't want that. I want to make sure I can get it out. But on the tactical side, I want it as soon as possible so I can avoid publishing it the other way.
Right.
And really, on these sort of latency sensitive needs, I think that's where the edge strategy really shines. Is I want it gives me the ability to make decisions as far out on the edge as I can, so I can correct problems as fast as possible. It preserves that shift left mentality. And if I have the ability to query across the whole system as a consistent state, it gives me that big picture of what's going on. I can do status reporting and that sort of stuff. And that's really where that use case shines.
Absolutely. And the comparison I make is when we were doing this vision for the future in regards to transportation, it's what you're saying is literally the difference between a car and a ship.
Yeah.
It's literally that difference. Is car is on land, it's very well connected. And you can have that, that your strategic kind of data flow immediately, on demand. You've got good connectivity, you've got good access to it.
And that connectivity can be a negative.
Yeah,
because now you have people spoofing that they're going to hit you and that sort of thing. Yeah.
And then you've got that, the maritime side, whereas you've got pro connectivity. So you want to keep it out there as long as possible, but you want to have the maintainability to get it when you need to. So I think, that comparison, it means that you have to strategically decide for certain locations which one to do, which one is the more positive side for each of those locations, depending on those aspects. For me, it's a pretty, I see it from a different perspective, from my experience in the past, looking at maritime shipping and looking into transportation, those side of things. That's where I've been more familiar with. And we're in the agriculture side of things, and the sensory for a scientific side. The only times I've ever been is looking at it from where I've seen drone maintenance, going and checking, using drones to go out and check that things are there as expected. That's where I've seen it being used. But it's very insightful. I've learned a lot from you today, and I really appreciate it. And I'm sure the audience have also been finding it interesting, because a lot of cases, many cases when we're talking about security, we're always talking about privacy and confidentiality. Right. But I think this really highlights that not everything is about encryption, not everything is about confidentiality, and that other types of programs and other types of technology does have an importance. That availability and integrity, the accuracy and veracity of that data becomes really critical. So it's really, I've learned a lot today, and a really pleasure talking with you and actually getting introduced. So I think my takeaways here for the audience is that not everything needs to be a secret and encrypted, and it really comes down to some areas of security is really about integrity and availability. So it's important to make sure that you, depending on what service you're providing, that when you take the CIA triad, you really understand how it applies to your service. So Mike, any thoughts, any key takeaways that you've gathered from today?
Yeah, I mean, I think a lot of that same stuff, right? I mean, it's just always nice to see those same security trade-offs and balances and availability, all of that. It's always applicable. Like, it's just different trade-offs, different things in these different environments. I always enjoy talking to Steve. We've been good friends for a long, long time, and so it's always fun to talk. Steve, any final thoughts or anything you want to part with?
I think it sums it up pretty well, and I think it's also interesting to note that in an environment where confidentiality is less important, the other aspects that, it's like an area graph that is grown on the other ones that you would, you don't get away from it. You have to spend more time on those other areas, it seems.
Absolutely. Awesome, many thanks. Steve, great to get introduced to you. I'm pretty sure the audience have really had a very enjoyable conversation from the discussion today, and I'm sure, like me, they've learned a lot. So it's great having you on the show. Look forward to seeing you on future shows and episodes to discuss more details. So again, this wraps up another 401 Access Denied. It's been fantastic and enjoyable for me. And again, for the audience, don't forget, tune in every 2 weeks for our latest episodes. Stay up to date. Send us your, what questions you might have for us. If there's topics you'd like to hear about, always free to connect with myself and Mike G on social media. We'll be happy to connect and get your feedback into input for future episodes. So, Mike, awesome chatting with you as usual. Steve, great to connect with you. And for the audience, stay safe and secure. Thank you.